Okay, we started recording. Hello everybody. Thanks for joining us today in our webinar about exploring the potential of genetically modified microbes. In our previous webinars, we told you a bit about genetic modification and biotechnology and its uses, and whether or not you've seen them. Now we want to take a step further and go into more detailed explanation about the application we are making, our own project, and also a bit more about biotechnology. So hi, I'm Samira, and this is Vicky.
Yeah, I am Victoria.
And we're part of the IGM team Amsterdam of the 2020 competition, and we're working together to make a beautiful project in biotechnology. And we hope that after this webinar, you've got more insights in how biotechnology is used and how genetic modification can provide solutions to real world problems. We start with a bit about previous knowledge. So we have one participant to be exactly. So I want to know how much or what kind of applications of biotechnology do you already know?
What do I know? Some products are made with biotechnology, but with an example. Do you want to know an example? Soya?
Yeah,
maybe.
Yeah,
I think a lot of fruits, tomatoes, so they are better resistant to bacteria. I think a lot of fruits are manipulated.
So more the food, genetic modification of food.
Yes.
Yeah. Okay, that's good. And how do you feel about using these products, using these genetically modified fruits or vegetables?
Yeah, it could be a bad side because you never know exactly what's happening after 50 years maybe, but at the moment it's helpful for providing food for the world.
Okay, good. Well, thanks for sharing this. We'll repeat this quiz after our webinar to see if you might have been learned or if your opinion has been changed. So please pay attention and also think about how you feel about the things we're explaining. Because what we're going to discuss today is, well, we want to have your opinion. So we start off and end off with a survey. We will give a short introduction into biotechnology and its current applications. And then we go more into detail in our own project, Forbidden Fruit, which is sort of in the design phase of biotechnological processes. And for every part of our webinar, we give a short presentation of 10 minutes, and then we'll have a question which can lead to a discussion. So you can think about how you feel about what we've just told and what you've learned. And that's also why we want your participation and we want your opinion in this. So we start off with a short introduction to biotechnological processes. Well, we have one biotech process, which is very well known and actually ancient. This is fermentation. So this is where the bacteria, it eats its food and then it makes product. And then you can all, of course, think of wine, yogurt, but also in what some more modern application is bioplastics or biofuels. And this is not the only biotechnological process. Nowadays, you also have a process called biocatalysis, in which the bacteria, it eats the food, then it produces a molecule, and that molecule is helping a precursor compound to convert a precursor compound to a product. So it's sort of a more step approach. And in this way, enzymes, for example, washing powder are being produced. In case of simplicity, and because this is the most common method, we focus on fermentation in this webinar. And why do we want this? Well, why do we want to do fermentation and maybe want to change these fermentation processes which are already used, for example, in yogurt, which is just a bacteria which occurs in nature? Why do we want to improve it? Well, actually, it's very easy. We can make different products. We can improve our products just very easily by genetic modification techniques. And this is way easier than in the changing the compound in chemical production. Because in chemical production, you have to take more steps to improve your product. Also, we can use renewable resources, where chemical production normally uses oil or some non-renewable resources. In fermentation, we use sugars, waste, oil, and there are even photosynthetic organisms which can convert CO2, water, and sunlight to a product, which is really cool. And this, the renewable resources are part of the lower environmental impacts. Using biotechnological processes is better for the environment, can be better for the environment, because we use renewable resources, we have minimal waste, and we use the energy we put in an optimal way. But why don't we all use biotech then? Well, there are some challenges, of course. One of the biggest challenges is to go from the small flask to big fermenter tank. Also, if you change the process, for example, the food you give the organism or the way you process the food before your fermentation, it has a very large impact on the process itself. And after fermentation, you need to process your broth, your resulting liquid to the product. And this has a low efficiency and has a lot of impact on the environment. Also, there's something called strain instability. We'll explain a bit more about this, but in essence, it means that after a while you stop producing your desired product. And because of the rapid technology changes, the need for new products, there is also a need for process design and modeling methods, which can fastly give you new ways of producing. And then we also have the economic feasibility. Oil is very cheap, while sugar is quite expensive. So it's actually economically more feasible to make, for example, biofuels to just use oil as fuel instead of making biofuels from sugar. And last but not least, we have public perception. And this is where you come in, because it's very important that people understand that we can use this technology in safe ways, and also in that we can improve the world with this. But people need to want the new technology, want the new product. So I will explain a bit more about the strain instability, because that's actually where our project comes in. Well, what is strain instability? Well, first, we have to start. When we have this cool biotech process, we have this microbe. And what this microbe does, it makes more of itself, it grows, because that's what all organisms want to do. And it will make a product. And the product makes us very happy. Well, the bacteria gets really happy of making more of himself, because that's its aim in life, as you can state. And because it uses resources, it uses food to make the product, it actually doesn't want to go in that pathway, in the product making pathway. So cells are a bit selfish. So what they don't like, they don't do. So after a while, they only grow faster, stop making products, and be more happy because they make more of himself. And that makes it's frustrating for us, because how can we solve it? But first I want to explain you a bit more about how this happens. How does this process occur? Well, when we have a microbe growing, there are always some slight modifications in the microbial chromosome, in the DNA, so in its genetic material. And some of these changes may increase growth and decrease production. So due to evolution, the faster growing strain will eventually outcompete the other. So it will overgrow producing microbes. So they will be really happy while the others will be just normal happy. And more happy is more better. And now this is a problem for us because we don't want to get frustrated because we're selfish as well. How do we solve this? Well, and that's a good question. Can you come up maybe with some strategies to overcome this strain instability? Ways of maybe very simple things you can do to force the microbe to do what we want?
If I have an idea?
Yeah, you have an idea. Think hard.
Why they still keeping making products, you mean?
Yeah.
The good environment, temperature.
To make it really comfy for the bacteria.
Yeah,
yeah. Yeah, that could be an option, just to make it so comfortable that it actually doesn't need to evolve because it has enough food, it has enough other nutrients, it's nice and warm, like that.
Yeah.
No, that could be a good solution.
Probably there's something else, but at the moment I have no suggestion.
Well, this is part of one of the solution, it is. So this is sort of where we jump to what we're doing. We are implementing one of the ways to sort of make the bacteria keep producing its product. And there are 3 general strategies, which can be the sort of the solutions to the strain instability. The first strategy is increasing genomic stability, which is sort of indeed making it very nice for the cell and making the genome more stable so it can't mutate. So you have this optimal way of making base pairs so they can't be changed or they're less likely to be changed. The second strategy is something called growth uncoupling. So we first grow the cells, and our production, we don't produce anything. After a while, the cells stop growing naturally, and that's where we start making products. So we have this switch which only turns on when the cell stops growing. So this is sort of what your solution is. It is, you first make it nice for the cells, it can grow, they have enough food, and then when they stop growing, you keep making it nice for them, for the cells, and you turn on your production pathway. This is called growth uncoupling, because you uncouple production from growth. And then the third strategy, and this is what we'll explain further, is called growth coupling. This is where the microbe eats food, we make it nice for the microbe, and then it will, in order to make more of itself, it also needs to make product. And Victoria will explain more in detail how this is done, because this has to do with networks. So we first will explain a bit about networks, and then we'll go in deeper in how we can growth couple, as we call it, the production with microbial growth.
Yes, so, okay. So we've been talking about this growth coupling, and to understand that, we will explain to you about what a metabolic network is. So first, what is a network? And we can define the network as a collection of dots, like we have here, which we will call nodes. So A, B, C, D, E, and F are our nodes, dots, and they are interconnected through a set of lines, as we see, and we will call those edges. So just like we see here. So now we can move on to what is a metabolic network. And to give you an example, this is how a metabolic network looks like. So it's very scary, right? And well, well, this is just as the example I showed you earlier, just a collection of dots that are interconnected through a lot of edges or lines. And these little dots and lines represent the chemical reactions that occur inside a living cell. So there are a lot of them. And now we can zoom in a bit, and it is still very intimidating. So this is just a piece of the network that we just saw, and it describes a group of reactions that are interconnected and are in charge of some specific task in the cell. But we still don't know why the word metabolic is in there. So let's dive even deeper. And we find a smaller piece of a metabolic network. So as I said earlier, the big network represents all the chemical reactions that occur inside a living cell. And now the reaction why it is called a metabolic network is because the dots or nodes are in this case representing what we call metabolites, which is nothing else but a fancy way of referring to chemical compounds. And the edges or lines are representing the chemical reactions that connect one metabolite to another. So this means that if there is a reaction that connects two dots or two metabolites, there is a chemical process by which one of the metabolites can be converted to another one. So in this example, we zoomed into the previous piece of the bigger metabolic network, and what we get are these ellipses that represent the metabolites and the boxes that give names to the lines or edges or arrows. So they are chemical reactions. And now, where do we find all of this information? So luckily, a lot of scientific research has gone into the identification of the chemical reactions that make up the metabolism of microorganisms. And all this information is available to us in online databases. So some examples are shown here, which are the database called CARE and the database called MetaNetX. And the example I showed you earlier is in fact coming from CARE. So now, why did scientists even bother in identifying these metabolic networks? So, well, thanks to this research, we can understand how microorganisms work. And microorganisms aren't nothing but cells. And then it turns out that cells are nothing but a collection of chemical reactions. So having a metabolic network of a microorganism is like having the plans of a machine, where you can see everything that is inside the machine, and that helps you understand how things work and probably where some reparations or improvements could be made. So now Samira already told us about genetic instability and how we can solve it. So we can talk about growth coupling, the production of our compounds of interest. What does it mean? So now we know that cells are nothing but a network of chemical reactions. Now, what is normally done in biotechnology to produce compounds in a microorganism is that an additional reaction that uses as substrate or food one of the metabolites that exists in the metabolic network of a microorganism is added. So in this case, the cell now has to use part of that substrate or chemical compound S to the production of a compound that it doesn't really need for growing. And that means that less of S is left for its own growth. And that causes what Samira explained us, which is genetic instability. So now what we want to do is to replace one of the reactions in the microorganism in a way that the reaction that we introduced will be the only one that the microorganism can use if it wants to produce what it needs for its own growth. But at the same time, this reaction will have our compound of interest as a byproduct. So in this way, the microorganism would not be capable of getting rid of this reaction because it is essential for its growth. And why is this better? besides having a reaction that is now essential for the microorganism, we are also left with our product of interest in a free form, which means that it would not be consumed by the microorganism since it doesn't need it for any of its processes, and that we can collect it for our own purposes. And since the microorganism would no longer experience genetic instability, the genetically modified cells can now be used in industrial settings for a continued production. So no more risk of mutation, or a much, much lower one. And so what is the role of our project Forbidden Fruits here? So first, we are basing our work in the fruits algorithm, which was developed in the microbial physiology lab at UBA, and it uses a different strategy to achieve growth coupling, which only allows it to produce compounds that are already part of the metabolic network of the microorganism. And since we want to introduce new reactions and thus new compounds, we are developing what we call forbidden fruits, where we say that this is forbidden, referring to the idea that the compounds we will produce are not naturally made by the cells, but they are non-native metabolites. And so forbidden fruits uses all that we have mentioned. It collects information about the metabolic networks and other chemical reactions from the databases, and then it provides us with a complete model of a microorganism and a whole set of reactions. And then within all this information, the algorithm can find the reactions that we could introduce in the metabolic network of the cell to produce our target compound. And it also tells us which reactions we would have to remove from the metabolic network. So it finds the optimal way in which growth-coupled production can be achieved in a microorganism. And now, how do we actually implement this in real life? Because all we have now is some advice from an algorithm. So that's when genetic modification comes in. The DNA of the cells contains the information about which molecules are produced inside the cell, such as enzymes, which are actually proteins that make the cell run different processes through chemical reactions. So then if we can modify which proteins are made by the cell by modifying its genetic code, we can also tell the cell which proteins to make in order to run reactions that we need, which are the ones that our algorithm will recommend, and which ones we don't want to have in the network in order to achieve growth coupled production. And that is how we can implement what our algorithm suggests. We make proteins that will run our reactions, and we eliminate proteins to eliminate the reactions that we don't need. And so, does it actually work? Because now it sounds like we have the solution for everything. So to prove if our algorithm is biologically plausible, so if it works, we will use genetic modification on these 3 microorganisms that are shown here to produce a list of compounds which are relevant in the industry for different applications. If what our algorithm finds is correct, we would achieve a sustained production of these different compounds in our different microorganisms. And why did we choose these compounds? Well, because they are widely used nowadays in a wide range of products. So having them produced in a more sustainable way, and potentially, in some cases, by the consumption of CO2, could promote a shift in production technologies in different settings. So now Samira will tell us more about this.
Thank you.
You're muted, Samira.
Okay, yeah, sorry. Well, we have chosen we have now chosen cool organisms to make our products. We've chosen this organism in such a way that they are well They're now commonly used in research and also in biotechnology, or we think that they have potential to be a new producing strain. But why these products? And what could be another product, and what do they do? Because salicylic acid, I've never heard of it before. Well, salicylic acid is, for example, a component of painkillers, but it has also antibacterial effects. So it can be used in cosmetics, skin creams and stuff, and in food as a food preservative. Mannitol, for example, it's used in medicine for some pressure against pressure in the eyes, and it's as actually a sweetener, low-calorie sweetener, which is a replacement for sugar. And then we have lactate. Lactate has great potential to be a bioplastic. It's very easy to make a polymer, like a big molecule of it, and to make, for example, flasks or other food packaging. Also, lactate can be part of some medicine, some liquids, and it's also used in some cosmetics to make it to make it solve very well and to make it mix well with other ingredients. So now we have all this information about what we can do, what we could achieve, and which compounds could be good for us, what could be good for the world. But are there any things, any compounds, any products which you think are good to be made with microorganisms?
Yeah, medicine, that you mentioned already.
Maybe something you use in your daily life, some chemical.
Would you like to have me using poo? Yeah, I think it's good for making a cheaper medicines, or still for food. Something else, I don't know. Yeah, fuel maybe.
Maybe also cleaning agents you use daily, or paint, or other chemicals where you're thinking like, I'm now buying this which is made in a chemical way, but I would like to have a solution.
Yeah.
Or
Maybe
sustainable.
Maybe something what the normal process is gives a lot of waste, so you can make a better production. So you the normal production. Do you understand what I mean? That you have you choose a production what normally gives a lot of waste, which you can reuse for something else.
Yeah, I think that's a great solution.
Something like that. But I was wondering, with the work, you said from okay, you can change it so that they make a production of your product because it doesn't need it for growing, but then it's not efficient for the microbe. Should the microbe then not change itself so it makes it more sufficient for himself? Because now it's making a product and that's not cost a lot of energy. Couldn't that Microsoft make a little bit change, so as evaluation of virus and bacteria, then they mutate so that the reaction is not more that you want?
Well, that's actually what we are doing. So what you were mentioning is sort of the classic strategy that indeed it's not needing the product for growth, but in the way which our algorithm predicts, we remove the waste for the cell to make more to grow only while consuming the food, by eating food and growing. Like if that's one pathway, like here, like in the red arrow, we remove this red arrow, so the only way to make more of himself is also making the product. We force it. It can't take a different path to growing.
So if there was so they will be less efficient than the normal bacteria. That's for sure, because the yes, some energy is being used to make the product. But if they are only on their own, like if they don't know any other way of growing, they only know this reaction, then they can't get rid of it. So they will just keep growing with this reaction.
Otherwise they die if they don't do it in a new direction. Yeah, okay.
Yeah.
Yeah.
Do you have any other questions?
No, I think I can follow I can follow it, yeah.
Great.
That's amazing to hear for us.
Because we're sort of biased while making this presentation. Everybody who has been checking it has been biased as well, so I'm glad to hear.
Yeah, I don't know if you have less information about this kind of stuff, if you can follow it. I don't know.
Yeah, that's hard.
Because it's a lot of information.
That's
but
true.
I can follow it, yeah.
Okay.
It's a good idea.
Well, then we have more questions for you.
Okay.
Because we would like to know if this information during this workshop maybe changed your opinion about microorganisms, about genetically modified microorganisms.
Yeah, I don't know. I'm still, I think, a little bit the same because you're changing stuff and you never know what's happening with the bacteria later on. But I think I still think the same, because if you could use plastics for making something that is perfect, because we now have a lot of plastics problem. But how should it be over 200-300 years? Aren't they eating a lot of other things you just use?
Yeah, but that's the thing with biotechnology is that probably these microbes will die if they won't be in a fermentation setting.
Okay. That makes a difference.
Yeah, because then the natural ones who are more efficient would win a competition, let's say. The evolution competition, the more efficient ones would win.
Yeah. Always still a little bit skeptical. Skeptic is not a good word, but a little bit reserveerd. How do you say it in English?
For sure.
Preserved, yeah.
Okay.
Well, that's good. That's good to know.
It's the first time we have this and that's quite nice. Like that we have an opinion that it's not in agreement, and that's nice.
But I think it's great if you could use plastics for, so you don't have then you have less waste.
Yeah, but that's not what we're doing yet.
No, okay.
Just making, for example, plastics with microorganisms, so we don't have to use oil, which is of course not which is limited amount in the earth, and also we can use CO2 to make products to, for example, make plastic. So we have this circular economy where we where we have CO2 being produced by burning fuels, and then we eat the CO2 with the microbes to make fuels, and then it goes round.
Yeah.
That's like the dream that we hope we can.
It sounds very good. We don't have less CO2 problems.
Yeah, or at least we can make them a little less, less
Make it
pressing.
more- yeah, and
Yeah, it's quite interesting. It's an yeah, if it works, it would be great.
yeah. That we're working day and night to achieve.
Yeah.
So to conclude it, to give a brief summary, we know that microorganisms can serve as an alternative for chemical industry. We know that there are some challenges to make it feasible, to make it efficient. One of those challenges is strain instability. And in our algorithm, in our project Forbidden Fruits, we've tried to come up with a solution to it, which is called growth coupling. And we hope that this in the end will make the microbe happy and will make us happy. And thank you for listening. Thank you for joining. If you have any feedback, I love to hear. We love to hear. And if you want to know more about biotech, we have some references here. Thank you.
Yeah, it's a good presentation, good slides.
Thank you.
So it makes it a lot. Now I know better what you're doing.
Yeah.
That's the purpose.
Yeah, and it is very interesting. And yeah, keep doing the good work.
Thank you. Well, I think then that was it for today. So thank you
Okay.
for joining. I will stop the recording now.
Yeah, thank you for their explanations.
And thank you for attending. Yeah, and for your